Just because two lines on a graph look similar doesn't mean one causes the other.
And the site digs into why these pop up, right?
Yeah.
It's not just random chance sometimes.
Well, chance plays a role, especially with data dredging, basically. If you compare enough random things, something is bound to line up eventually just by luck.
Ah.
But other reasons include a total lack of a plausible way one could cause the other. Or maybe both variables are just increasing over time independently. Or visual tricks, like weird y-axes on graphs making things look more dramatic.
Or maybe there's a hidden factor.
That's a big one. A confounding variable. Maybe something else is causing both things you're looking at to change. The point is, the two things you're correlating don't have a direct causal path between them.
So the core idea in statistics is the connection looks real statistically, but it's not a genuine causal connection. It's spurious.
Precisely. It's an appearance of connection without the substance of causation.
Okay. Law statistics.
Yeah.
Now for the really cutting-edge application.
Mm.
Machine learning and AI. How does spurious fit into building systems that learn from data?
This is where it gets really interesting and maybe a bit messy. ML models are all about finding patterns, finding correlations in massive amounts of data. That's how they learn.
Right. Let the numbers speak for themselves.
Kind of, but the problem is they're so good at finding correlations, they often pick up on ones that exist only in the specific data they were trained on. Correlations that aren't the ones we actually want them to learn for the real world.
They find patterns, but not necessarily meaningful or causal patterns.
Exactly. Trying to get ML models to learn truly causal relationships just from looking at data is notoriously difficult. They tend to grab onto whatever statistically predicts the outcome in the training set, even if it's, well, spurious.
So spurious in ML means the model learned a misleading pattern again. But it seems more complicated here.
It is, because ML researchers found that just saying, oh, that correlation the model learned as non-causal wasn't enough. It didn't fully explain why the model failed or how to fix it. So the research paper we looked at points out that people in ML tend to think about spuriousness along several different lines or dimensions. It's not just about cause and effect. It's also about things like relevance, how well it generalizes, whether it acts like a human, and crucially, whether it's harmful.
Multiple dimensions. Let's unpack those. Maybe start with those classic examples they use, the cow and the camel one.
Perfect example. You train a model to tell cows from camels. But maybe most of your cow pictures have grassy backgrounds and most camel pictures have sandy backgrounds.
Okay.
The model might just learn green background means cow, yellow background means camel. It ignores the actual animal. That correlation background color to animal type is spurious. It works on the training data, but it's not based on the animal's features, which is what we intended. The background isn't causally related to the animal's species ID.
Right, and the pneumonia detection one.
Similar idea. A model looking at chest x-rays to find pneumonia might learn to detect, say, a little metal token that technicians place on the patient during the scan.
How would that help?
It doesn't for finding pneumonia. But maybe different hospitals in the training data put the token in slightly different places, and maybe those hospitals also happen to have different rates of pneumonia cases.
Ah, so the token position gets correlated with pneumonia just because of how the data was collected.
Exactly. The model learns that spurious correlation. The token position obviously doesn't cause pneumonia, but the model uses it as a shortcut because it worked in the training set.
Okay, those definitely show the problem. So what's the first dimension researchers use to label these kinds of correlations as spurious?
The first one is relevance. Basically, the model latched onto features or patterns that are not relevant to the task the developer actually intended.
Like the background color instead of the cow, or the token instead of the lung issue.
Right. The learned correlation uses irrelevant information for the intended task.
But relevance can be subjective, can't it? The paper mentioned an example with a fish. A tench.
Yeah, the ImageNet tense example. It's often a picture of a fish being held by a person. If the task is just label this image tench, maybe only the fish features are relevant. But if the task was broader, like scene understanding, the person holding it is relevant context.
So what counts as relevant really depends on what you decided the model was supposed to be doing.
Exactly. Developer intent, task definition. It shapes what you consider relevant versus spurious.
Okay, relevance, dimension one, what's number two?
Generalizability. This is a big one in ML. It means the correlation the model learned works fine on the training data, but it breaks down when you show the model new data or data from a slightly different environment.
It doesn't hold up in the real world, basically.
Right. We say the model overfits to the training data. Those correlations that are specific to the training set and don't generalize are considered spurious.
Like the pneumonia model failing if it sees X-rays from a new hospital that puts the token somewhere else.
Precisely. The token pneumonia correlation didn't generalize. The goal is usually models that work reliably out in the wild or under natural distribution shifts. But defining what that means can be tricky itself.
Okay. Relevance, generalizability, third dimension.
Human likeness. This is about whether the model uses correlations or strategies that a human wouldn't use for the same task.
So if a model identifies objects based on texture, when humans mostly use shape, that texture-based approach might be seen as spurious.
That's the idea. The goal might be for the AI to not just get the right answer, but to get it in a way that mimics human reasoning or perception. But again, it's complicated. Human perception isn't uniform.
Right.
And do we always want AI to be just like humans? Sometimes we want superhuman performance, or we want to avoid human biases. So human-like isn't always the ultimate goal.
Which brings us nicely to the fourth dimension. Harmfulness. This feels really critical.
It is. This is where a learned correlation is deemed spurious, because relying on it leads to unfair outcomes, reinforces negative stereotypes, or causes the model to perform poorly for certain groups of people.
Even if the correlation sort of reflects something in the training data, or even the real world.
Yes, that's the crucial part. For example, historical hiring data might show a correlation between gender and getting hired for certain roles, perhaps due to past bias. If a recruiting model learns and uses that correlation.
Like the Amazon tool that was biased against women applicants.
Exactly. That correlation is considered spurious in the context of its harmful impact. Gender isn't causally related to job qualification, but the model picked up the bias pattern. Relying on it perpetuates harm.
Other examples like voice assistants not understanding certain accents, or facial recognition failing on darker skin tones.
Yes, or AI image generators defaulting to stereotypes doctors are men, nurses are women. Or toxicity detectors flagging words like gay or lesbian just because they appeared near toxic language in the training data.
So even if a statistic is true in the world, like maybe more nurses historically are women, using that correlation in a model can be harmful if it reinforces stereotypes or leads to unfair treatment. So we call that correlation spurious.
Right, because the connection itself, e.g. gender to profession, isn't the causal factor we should be using for the task, like evaluating skills, and relying on it causes harm.
Wow, okay, so in ML, spurious is way more than just not causal. It's this complex judgment based on relevance, generalizability, human likeness, and potential harm.
That's the key takeaway from the ML perspective. It often involves a subjective call by the developers or users about what makes a learned correlation good or bad, genuine or spurious, based on the goals and values for that specific AI system. It's often, as the paper says, in the eye of the beholder.
So let's recap this journey. We started with a simple dictionary idea. Spurious means false, not genuine.
Then we saw its very specific practical legal meaning in Colorado property law, a tool to fight fake or baseless claims.
Then jump to statistics, where spurious correlation is the classic warning. Correlation isn't causation. Don't trust connections that lack a real causal link, no matter how nice the graph looks.
And finally, in machine learning, we found spuriousness is this really rich, multi-layered concept. It's about models learning correlations that fail us. Maybe they're irrelevant, don't generalize, aren't human-like, or, importantly, cause harm.
Understanding these different facets of spurious feels incredibly useful. It helps you critically evaluate information, whether it's a legal document, a news report citing statistics, or interacting with an AI. It's about developing that instinct to question if a connection that looks real actually is real and right for the context.
Definitely. And it leaves us with a really big question, doesn't it? Especially thinking about AI. If what counts as spurious in ML often depends on human judgment about relevance, harm, and what we want the system to do. In a world that's going to rely more and more on AI finding patterns for us, how do we collectively decide and then ensure that these systems are learning the right kinds of correlations and ignoring the spurious ones, especially when the definition itself can be subjective?
That is a really provocative thought to end on. How do we define and enforce the right correlations for our AI? Lots to think about there. That's our deep dive for today.